will talk today about detection of moving charge by position-dependent qubits. And also I will try to touch the aspect of possible measurements of position and momentum of electron at the same time. All right, so let me go to overview. So I will basically describe the basic principles of coding of quantum information by means of position-dependent qubits. So in such case, the linear functions are used, and most schemes of quantum technology implementation are relying on encoding of quantum information in eigenenergy basis. So that's a kind of new approach. And so I will mention a few things about quantum gates, and then I will try to show you how to measure the movement of electric charge in this space in position-dependent qubit. So there will be some applications that can be used for a beam diagnostic in CERN experiment, for example. It can be also used in solar wind measurements. Yeah, so we will see what's the prescription for construction of new type of quantum detector. All right, so let me move forward. So basically, if you observe this kind of community that is dealing with implementation of a quantum computer, you have the key players. The key players are IBM and Google, and they're using superconductor technology. So essentially, they are dealing with Josephson junctions, and this type of electronics, superconducting electronics, has this feature that there's very low number of noise. But still, the structures are quite spacey. So, like if you have a traditional superconductor, then you have a so-called superconducting coherence length, and this superconducting coherence length is usually like 3,000 angstroms in PB. So this simply means that this is like 300 nanometers, and you cannot go to smaller sizes. So in a sense, there is obvious limitation in the size of Josephson junctions. So this is one of the obstacles in development of highly integrated circuits. And second obstacle that is also technological obstacle is basically that in order to control the state of superconducting qubit, you need to use a vector potential, or more or less, which of course is reflected in, because you can translate this to magnetic field that acts on the given qubit. And basically, in practical way, you are creating waveguides, and there are usually the gigahertz frequencies of waves, and these waveguides also take space, so you cannot put too many inputs and outputs to one chip. And this is another limitation of implementation of a quantum computer. So basically, people end up with a system that has like 50 or 70 qubits, and that's it. That's very hard to go further. So because of those obstacles, there is some saturation of possible progress in superconducting electronics, and there is a nice alternative, and the alternative is to use coupled quantum dots. And so basically the idea is that you are going to a CMOS technology, and in CMOS technology you have source and drain, and then there is a gate on the top, and you can control the connectivity of source and drain by voltage that we apply to this gate. In those days, people do amazing things. So it's already produced. There are already chips produced where this length of this channel is only 3 nanometers in length. So more or less like 30 atoms only. So definitely, and this chip is already available commercially. Like there's a company with name of Silicon Creativity in Krakow that already makes such designs of circuits with such technology. So the central idea is that you inject electron to one of this quantum dot, single electron, and there is, so you can model this system by effective potential, and simply this electron will go back and forth from quantum dot A to quantum dot B. So source and drain will play a role of quantum dot. And there, if the system has at least two energy levels, there are characteristic oscillations of occupancy, and this is the normal state of the qubit. So basically, you can encode presence of electron on one of the sides, like logical 1, and on another side as logical state of 0. So in principle, you have superposition of those two logical states, and it's natural to identify the quantum state as spanned by two maximum localized wave functions. There are Wannier functions, left Wannier function and right Wannier function. So basically, once you have the state of the qubit given in such a way, there's a presence of electron between A and B, as seen on the right side of bottom picture. And if you lift the potential in metallic gate 3 and 2, so if you lift the potential in metallic gate 2, you will see two parts of a wave function coming. So they will correspond to determination of A square and B square. So in such way, you can determine A square and B square experimentally, or you can simply, if you lift the potential on metallic gate 3, you can cause wave packets to propagate further, and simply you can have this interference between A and B, and simply you can measure the difference in phase between A and B. So in that way, you can conduct the measurement of this qubit state. So that's a prescription. So such work was firstly started by Fujisawa and Peta, and it is under study. So I already constructed analytical model for n-body system of interacting electrons in tight binding approach, and now I'm trying to extend this approach to account for various effects as decoherence and so on. So I will show you on coming slides how things are developing. All right. So basically now I will come to this idea of detection of movement of external charge. So basically, first observation is, okay, so we can have external nanowire or accelerator beam. So there's a movement of charge. And in classical case, there is a feature. So if there are two such qubits or two systems of a kind of quantum dot structure, so then this ground state is made from electrons that are in anti-correlated positions, simply because of Coulomb repulsion force brings the system to occupy such lowest possible energy. However, this ground state is changed slightly in case of quantum regime. So obviously there is a possible equal coexistence of electron here and here. So as you can observe from tight binding model solutions. And basically, if you have two electrons in a ground state, if there is a passage of external charge, obviously it will bring excitation to this ground state. So you can detect the phase imprint on this qubit, and you can see how this charge configuration was changed. So I will try to describe this on a couple more slides. All right, so that's a central idea. So you have a initial potential that is gray one, and there is the wave packet of a single electron is trapped, and then where is this movement of charge, this potential is going to be renormalized by external moving charge, and obviously you will see a slightly different state of a qubit afterwards. So you can say this is like a kind of weak perturbation to the state of qubit, or weak measurement. That's a kind of nice example of weak measurement. So actually when moving charge has mass similar to electron, this passage of external charge close to a semiconductor qubit will also change the state of this passing particle, and so that it can be slightly deflected and it can have a slightly different dynamical state. So however, if you use, for example, heavy protons and you have electron, you can, in first approximation, assume that the state of proton was almost not changed. You can treat this passage of this particle in a kind of quasi-classical way, and you can treat the state of qubit in kind of quantum way. That's a kind of general intuition. All right, so basically, yeah. So my description will refer to the usage of tight binding model. Nevertheless, you can describe this problem by Schrödinger equations. Like you can end up with integral differential equations, Schrödinger equations, that also can describe you this is a kind of weak coupling of two charges, right? So there are various possible schemes. Obviously, you can also use Dirac formalism and so on and so on. And also, you can use propagator formalism and so on and so on. Okay, so yeah. So basically, I have in order to identify the state of a position-based qubit, I have defined so-called correlation function. So if in a classical case, if you have two interacting qubits, it may happen that electrons are in anticorrelated state, as on the right side, or in the case when they're in correlated state. So so I will call it this. So there are two possible correlated states. So this one on the left side. This is n++, or both electrons on the right side. It's also possible that both electrons are on the left side, and it will be n-, and this state will be called n+, n-+, and also reverse state could be n-+. So basically, this correlation function is like n++ plus n-. So it's like number of cases in a correlated situation minus number of cases in anticorrelated situation over total number of cases. So this is very simple correlation function. So yeah.
Question. Before you go to correlation of two qubits, whether I understand this one qubit, you said we can make measurements, so we determine a square modulus of a square plus b square, and then we can do another measurement to determine the phase difference, right? Phase difference, I understand, between B and A, yes?
Yes.
Okay, so essentially you mean that you can determine the state, okay? Because you determine phase difference, but not the absolute phase, of course, right?
Yeah,
so
of course.
It's determination of the state. Now, okay. So now my question is whether when you do this determination, it is such that the state is not changed by this, yes?
Yes.
It's still the same after determination, or not?
Well, I would say, well, sooner or later during this project, well, I think it depends on the detailed measurement scheme that can be used. So, well, I would say you have to repeat this measurement n times, right? It's quite clear, right? Or let's say 2n times, because you have a state of qubit. So either you lift up the potential metallic gate 2 and metallic gate 1, and then so you either determine a square and b square, or you unlift potential metallic gate 3, and then you only determine this the phase difference. I think it would be very troublesome to be able to determine output 1 and output 2 at the same time. Nevertheless, from formal point of view, you can try to attempt doing so. The problem is that, okay, so in output one, we have two wave packets, like one associated with a square and second wave packet associated with b square. And so I think if you measure first, let's say b square, this might affect a square, right? Or you can try still guide it. You can try to guide it into two paths, but still, I would say, I mean, that's quite a tricky question, because in principle you can also design some other parallel lines and try to shoot some electron that is partly reflected, from A and B, right? Mm-hmm. But yeah, so I would say, so this was just one of ideas how to do it, but I have to say that it would be very nice to analyze this problem deeper and deeper. So it was just a kind of first type of nanotechnological scheme that come to my mind. This picture which you see.
The answer to my question is not so evident, right?
Yeah. I admit that your question is very tricky and very deep, and it would be nice to do things to write down this measurements process by projection of some operators, right? So
yes.
Yeah, so I would say it is worth of trying to formalize this deeper. And I always believe that this measurement is more or less, this is connected with interaction, obviously, right, with external systems. So for the good question is which external system shall be chosen? Whether we shall choose already well-defined system as Josephson junction, right? Or we shall use another types of a quantum dots. That's still, I would say, the thing that needs to be debated in more detail.
Okay, thank you. You can continue.
All right, thanks. All right, so there are these correlation functions, and obviously in this in case of classical system, there is only one scenario possible. So either the system is correlated or anti-correlated, while in this quantum case there is a superposition of states. So the mixed situation is possible, and then these further details can be extracted from this. Then the further details are described in this paper. All right, so so basically this so there is a velocity of this probing particle. This is one of the scenarios. So you see the velocity is changing its sign. So particle is reflected, and there is an acceleration of this probing particle. That is this moving particle that is affecting the state of a qubit. And basically we have in such case we have a single electron correlation function of such dependence. So you see this is pretty complex value. So basically positive values means that the states are correlate. Just coming back to this definition, so this positive value means that states are correlated, and negative values means that states are anti-correlated. So you see this dynamics of the system starts to be pretty complicated. All right, so now I would like to briefly describe this system by this Hamiltonian approach. So I will choose this so-called tight binding model. So I would say it's a little bit, so you can see the system as two coupled resonant cavities, right? So the wave or a particle is either in left cavity or in right cavity, and those cavities are kind of connected. So you have a localized energy in a one cavity. This is AP1. This corresponds to this left side, and you have localized energy of the right cavity. And there is some hopping energy from left to right. So this corresponds to a hopping electron from the left to a right quantum dot. This model turns out to be very powerful from point of view of predictions because it's very simple. And at the same time, you can treat this model as a simplified version of Hubbard model. And Hubbard model, as you know, is very general model in condensed matter physics. So so obviously the most type of general description would be with Hubbard model. That is still not the most general model. The most general model in such type of system would be an interacting particles in Schrödinger description. But obviously, it's very hard in practical way to solve it, since we are dealing with integral differential equations, and even more general description would be Keldysh formalism that I'm not going to describe today. All right, so this is tight binding model. So and now there is evolution of a quantum state, and there is one characteristic thing, that this moving particle is going to affect this Hamiltonian. So I just modeled this by Dirac delta function. So essentially, this presence of particle on the left side are affected. So if particle is in the closest position to a position-based qubit, if this moving particle, external moving particle, is in the closest distance, there is time t1, and then this effect is the strongest. So obviously I can model these things by Gaussian, as kind of Gaussian-like function, but to be very simple, I just model this function as a Dirac delta function, right? So there's like a kick to this state of this position-based qubit. So I have AP1 plus V times Dirac delta function. So this is change of occupancy of on the left quantum dot. There is a change of occupancy on the right quantum dot, is AP2 plus V2 times the Dirac delta function, and there is change of hopping probabilities. So here is this TS12 plus some complex value, and here this Hamiltonian, which is given by equation 2, is described, how to say, in Hermitian way. So this is not doesn't have to be fully true. So in principle, the effect of this external passage of external flow of charge could be that partly the quantum state of position-based qubit is partly move away from this state of two qubits, the two quantum dots. So what I'm saying is that in most general case, this V1 and V2 can be of complex value, and here we can have V3 plus V4, and here we're supposed to have V5 and V6. So in general case, this impact of external moving charge will be that this evolution during this small time step will be no longer unitarian, right? So you can end up in such situation where let's say the sum of two probabilities for electron being in a left and right quantum dot is below 1, right? So part of the wave packet was delocalized. So this is most general situation. Okay, and then there's a prescription how to compute this AP1, AP2 coefficients. So this is like Wannier function. So this sort is supposed to be Daga here. So Wannier function of the left side. So you can move from Schrödinger description to tight binding model using these formulas. So Wannier functions are a linear combination of two eigenenergies. So it's maximum localized wave function of electron on the left side and on the right side, and there is a hopping probability TS1. That's a prescription. All right, I will move forward. So obviously, maybe one more thing. Obviously, here there's effective potential, and this effective potential comes from this voltage polarizing gates. So in initial picture, I only have a gate 1, but in practical way, I can have a gate on the left and right side. So those 3 gates are generating this effective potential. So you can imagine that if there's a passage of external particle, there is additional added potential for a moving particle. So this is a full prescription how these parameters will change with time when we use this tight binding approach. Okay, we move on. Yeah, so essentially, now this is a kind of elementary exercise as kind of like we do one of the exercises that we do during a quantum mechanical course, is that this there will be some discontinuity because of this Dirac delta function. There will be some discontinuity of changes of this quantum state at time t1, and obviously we end up with such type of formula. So clearly we refer here to this values of this v1, v2, v3, v4. So this like values of renormalized potential due to presence of external charge particle, right? That's how we deal. So we have a change of a quantum state, a kind of sudden change of quantum state, especially in accelerator when there's a passage of proton that is close to the speed of light. This will affect the state of a qubit, and of course, if you have thousands of protons in a beam, still they will extract. You have to add up these processes together, right? So simply you can get certain matrix that describes this transition, and this matrix is just a matter of simple algebra. All right. So basically you have a quantum state. So then the conclusion would be that what will be changed, since you can parameterize the quantum state by occupancy of eigenenergy A1 and A2, and by phases that are connected with this by the 2 phases. So then simply the passage of external charge will change the values of CA1 and CA2 coefficient. So it's like occupancy of eigenenergy levels, and also will change the phases. So it's quite intuitive to expect that there will be some phase imprint on this qubit, since this moving charge is generating time-dependent vector potential, right? All right, so you can characterize those phenomena. So it's a little bit lengthy algebra, but this is a kind of prescription. So this is the state after the measurement, and then you can get the values of those coefficients in fully deterministic way. This is elementary relation, nevertheless it's a bit lengthy, so I will maybe skip more detailed discussion on this. All right, so to give you further taste of possibilities. So obviously we have a situation where there's a passage of well, when we can change this state of a qubit, but obviously we can also construct a kind of quantum logic using this anti-correlation principle. So imagine just more simple case. You have just let's refer first to classical situation. You have 2 charge balls that are in some boxes. So obviously the ground state, this ground state of a system, we will prefer that there will be anti-correlation of charge balls, since such configuration minimizes electrostatic energy. So this is a classical swap gate. But if you move from description of electrons, from description of a charge balls like billiard ball to a quantum electrons, obviously this state will be more spreaded. So then you have to account for this for this quantum mechanical description. So obviously this system can also incorporate this quantum swap gate implement. So this can implement quantum swap gate. In very similar fashion, you can construct controlled NOT gate. So this is like a NOT gate. So control NOT gate is again the same concept. Plus there's a control bit or a qubit, control qubit. So when there is external charge ball, it can vary the state of NOT gate, right? So then you can still have a CNOT gate. This is classical CNOT gate using charge balls, billiard balls, or when you go to the size of CMOS transistors, you can think about implementation of a quantum gates, quantum CNOT gate. All right. So again, here you can apply this linear function approach. Just to give you a few characteristics connected with this position-based qubit. So there's a probability for electron to stay on the left on the right quantum dot, and this probability is given by such equation. So there is a time-dependent factor. This is cosine A2 minus E1. So this is energy difference between two levels. Obviously, there can be some additional phase added. So you see this oscillates as it was described before. Okay. Then obviously you can think about implementation of other gates, quantum gates, and then you are asking the question, what's the phase difference between the left and right quantum dot? And it turns out this is such equation as given here. So that's a kind of, there is a phase dynamics of phase difference that is naturally built in this tight binding model. All right, then there's a question how to implement more complicated gates or other quantum gates. So how to implement phase rotating gate? So well, if your state is localized here, so this is it's spanned by 0 and 1 by two linear functions, then you can have pulse of external current flow, and this pulse of external current will generate some additional phase imprint on this qubit. So this is one way of controlling there's a phase, this phase difference, right? All right. So another way is to use. So before I used Aharonov magnetic field, so vector potential Aharonov-Bohm effect, and also I can use electric version of Aharonov-Bohm effect. So if I have a position-based qubit, if I have the same bottoms of potential, the wave packet is evolving in the left and right quantum dot with the same speed. However, if I lower one of these bottoms of potential, then I will get a different speed of evolution of a wave packet, and then this difference can be scaled by this ground. So this is VG1 and VG2. So this can be scaled by such integral. So what it's possible is that you might wish to make some phase imprint in electrical way on a given position-based qubit. So you have to lower one of the ground states and push the wave packet to be in this ground state, and then you can evolve for some time, and again you have to recover this state of the system. So that's a kind of general prescription. All right. So then there is also another issue. So if you have this two different bottoms in effective potential, what is possible is that you might push state into more localized state. Obviously, if you push the electron to stay in the right value of potential, then this electron cannot move deeper, so it's kind of localized. So this is one of the way of localization of the wave packet that you can do. And obviously, if you if you will shine with some radio frequency signal, then you can populate eigenenergies A3 and 4, and so this localized state will be transferred to delocalized state. So there are such possibilities. So I would say at this stage, the best what you can do is to be able to determine the position of electron only to one quantum well. Well, it also depends how exactly you are able to shape this effective potential. That's another issue. All right. So and then there is a possibility. So in a sense, the same structure which was described at the very beginning can implement the position-based qubit. This I call it Wannier-based qubit, as two Wannier functions are used to code quantum information, and then it's a possibility that we can transfer this quantum information into eigenenergy-based qubit. So basically, there is a chain of transformations of a potential that can bring that certain. So here there was the information was encoded in position-based qubit, and then it's transferred into eigenenergy-based qubit. So essentially, this electron will populate the ground state, localized state, also this excited state. All right, and so basically, I just want to underline that there is a possibility for construction of the whole logical circuit, in both schemes using the same nanostructure. So that's a kind of universality of this nanostructure, and also this scheme is very much of interest of semiconductor industry, since the CMOS is still developing. Okay, yeah. So there are possible transitions of a wave function. Maybe I will skip this part. It's when we move from dirty position-based qubit to eigenenergy-based qubit. Okay, so there is a possibility of now how we can take into account this two electron system. So basically, one of the approach which is this for two interacting particles is by using of this such type of ansatz, and then by integrating with respect of one variable xb or xa, we get the set of two coupled integral differential equations. So this integral is supposed to be in the front. Yeah, then we need to solve it. So this is the way of dealing with in very weakly interacting charged particles with usage of Schrödinger formalism. However, this is, you can imagine, this is not necessarily the most general, since this scheme. So this is like treating of two particles as almost kind of independent. So this approach is not, it's just approximation. It's not a deep solution to this problem. Okay, so basically we can also inject two electrons to this nanostructure, and then we can make a measurement on one of the particles. So we can place external moving charge in such a way that it will affect one of the particles closer than more than another particles, and then this will have these projections, and so that there will be weak measurement done on the state of this position-based qubit. We can also, this is a very interesting case, we can also go into a description of Roton-based qubit, position-based qubit. So essentially, it's a bit analogical to quantum state to qubit to superconducting qubit. So that there is barrier here. So obviously, you can construct such type of qubit also in nanostructures, in semiconductor nanostructures, and then you can place one barrier or two barriers, and you can tune the state of qubit, but by both magnetic field and electric field, and I will describe this in a greater detail. So then, in such case, there is another scenario possible, An external moving charge will not only change the distribution of a wave function, but then there's a quantization of magnetic flux in such type of system. So moving charge can change number of fluxons present in the system. So this could be situation a bit similar to the case of superconducting technologies, where such effects can be spotted. Okay, and now the more tricky part. This is case of interacting qubits, position-based qubits. So if you have two lines, I call it. There is a paper with title "Analytic View on Coupled Single Electron Lines." So I view those two parallel lines as two coupled single electron lines, and there is a possibility for electron presence at node 1, 2, and 3, and again for another electron at 1 prime, 2 prime, 3 prime. And it turns out that it was quite surprising that such a system can have analytic solutions. And yes, I characterize those solutions using the simplistic tight binding model, which I will describe you in more detail. If you look on the system from electrical circuits point of view, it requires such CMOS transistors as given here. So there are transistors, and there is a capacitive coupling between them. This is more or less the equivalent circuit for such type of structure. Actually, reality can be even more complicated, but I'm not going to tell you in greater detail on that. It's very important to note that you have controlling signals, electrostatic controlling signals. So you have ability to construct nanowires that are not so spaced as waveguides in superconductor. And so there is a big chance you can really pack a lot of quantum information in small size. So you get by these voltages V1, V2, V3, V4 that you apply to the gates, or V1 prime, V2 prime up to V4 prime. What happens is that you can tune the effective potential in which this one first electron is placed, or here. So you can electrostatically control it. So you can also inject more than one electron. So you have ability of conducting various types of experiments in this nanostructure, and there is very nice concept of programmable quantum matter that somehow goes with it. So that's why I believe that such proposed implementation of CMOS qubit, single electron qubit, is very promising both for applications and for fundamental experiments. All right, so let me move on. So yes, so in general case, you can have a chain of coupled quantum dots. You can turn on or turn off them electrostatically simply by. So this is very simple. So this electrostatic control means simply that. Okay, maybe you just by metallic gate, whether you can disconnect to areas by certain voltage applied to the metallic gate. So in that sense, you can control. You can have time-dependent quantum graph. That's what I'm trying to say. And this is also in my recent cryogenic paper that was published this week. That then the scheme is described in most simplistic way. So this gives you the possibilities. And so my prescription is very simple. We simply treat qubit or a chain of qubits as our quantum detector, and then we can obtain weak measurement by monitoring the state of qubits. So this is weak measurement is probably the most delicate type of measurement that can be done. So yeah, so okay, so we can have a band structure as in solid state physics just by changing the size of qubit. A plus B is the size of distance between left and right quantum dot. So this is you can go from the case of so this is the case of insulator. This hoping. So so you have two single electron lines. The hoping between left and right quantum dot is going to 0. So this is like isolator. And then by increasing this hoping, this T1, and then you get a different band structure. So that's quite essential that you can tune this band structure just by electrostatical control on the voltage of gates. All right, so okay, so let me move on. So then the simplest case of two-qubit interaction is given by such interaction matrix. So you have electrostatic energy on this diagonal. So there are two symmetric qubits in parallel. There is distance between them d1, and there is the distance between left and right quantum dot is a plus b. So this is quite simple Hamiltonian, and then you can get evolution analytical solutions, and thus you can have full knowledge on the evolution of the system. So in particular, you can monitor the electrostatic entanglement. By this electrostatic interaction, there is entanglement that is emerging between those interacting qubits, and there is von Neumann entanglement entropy SB that can be obtained, and I give you a few examples of that. So basically, you have entanglement entropy that is time dependent, and the evolution of this entropy is strongly depending on this hoping. So this is hoping in a TS1 in a qubit in the first qubit, and TS2 is a hoping in the second qubit. So so you see if hopings are the same, the entropy is constant. And if they are different, as this in this red line, the dynamics of this entanglement entropy is much different. So you are going to get various dynamics of a quantum entropy for various types of hoping values for qubits, for interacting qubits. That's quite interesting. So you can control the entropy by controlling the hoping kind of constant or hoping parameter, and you can so obviously you can also change this hoping parameter in time domain. So that's why you can control this electrostatically, this entropy with time. Right? All right. So the correlation function also has a nice feature, analytical feature. Here the explicit formula is given referring to this two-qubit interaction. So there is a PE1, P2, P3, P4. That's an occupancy of eigenenergy level 1, 2, 3, 4. And TS1 and TS2 are different hoping constants for different qubits. So there's a nice landscape of behavior that is much richer than in case of classical two interacting charge balls, I would say.
May I ask a question?
Yeah.
You wrote this formula for quantum entropy, and it was a density matrix. Why
Right.
you have mixed states here? What is the reason for that? Rho is a mixed state, it's not a pure state, right?
Yeah. So the thing is that the mixed. So in accordance with my knowledge and with my observation is that, okay, if you have isolated qubit, usually you don't deal with a mixed state. But when you have two interacting qubits, electrostatically interacting qubits, then if you only observe the state of one qubit by reduced matrix, then simply you see that this,
Right.
this becomes
Okay.
mixed.
Okay.
That's my observation. But
reduction, right? Okay.
yeah. So yeah, in general, quite recently I developed the concept where this concept is of complex time that can also describe the coherence effects, and yeah, so I will get more kind of general formulas quite soon. So in that sense, I can have also this this ability to parameterize this various type of decoherence effects. Okay. All right. So again, we can place the system in external radio frequency field, and this will so we have a cavity, quantum cavity. We have a qubit, an interaction between qubit and cavity, James coming Hamiltonian, and then there's a possibility of having this Rabi oscillation in position-based qubit. I will not describe this in detail. There's one of my paper. It's entitled "Towards Quantum Internet and Quantum Communication in Position-Based Qubits." You can read it. It's pretty lengthy. There is a lot of technical aspects included. Yeah, it also gives you a philosophy how to populate or depopulate some eigenenergies in position-based qubit. Okay, so I will move on. Okay, now that's probably one of this. So I have this great pleasure of listening to Professor Arkadiusz Jacek talk this Tuesday, and there was a question about possible co-measurement of electron position and momentum, and obviously X operator, position operator, is non-commuting with momentum operator. So this basically is a hint that those two observables cannot be measured at the same time, or at least measurement of one observable is causing this disturbance in determination of another observable, and so on. So basically, I was thinking about such type of experiment that you have this Josephson junction. This is superconductor, isolator, superconductor. And Josephson junction is excellent in measurement of all changes of magnetic field. So what I'm saying is that simply like in superconductors, if there's a critical voltage superconductor can overstand, and it still maintains its superconductivity state. Usually it's in millivolts, like 2 millivolts per superconductor. If you exceed if you apply bigger voltage than 2-3 millivolts, most superconductors lose superconducting property. And so basically, a superconductor is able to voltages that you've observed in superconductors, as observed by Dr. Marcin Kowalik, my previous speaker today. So they were in range of microvolts. So what I'm saying is that movement of electron. So the prescription is simple. You have two quantum dots, semiconductor quantum dots. You place the electron. This electron oscillates between left and right. Oscillates. During this oscillation, the electron is generating this vector potential that is affecting this Josephson junction. So in a sense, this vector, the momentum of oscillating electron between two quantum dots is reflected by a phase imprint on this Josephson junction. That can be also a qubit. So so what I'm saying is that if you are having the localized state, so just to so localized state, just to give you this description. Yeah, so the localized state was corresponding to the presence. So it could be by occupancy energy level 1 and 2 here, right? So if you still have a you know, if you populate two energy levels, there will be some oscillations, but just in the range of this one value of potential. So what I'm saying is that, so in principle, you can try to measure both position and momentum of electron here. So you will measure the momentum by the state of Josephson junction, and position. Well, that's you have predetermined position of electron in a certain range of in a certain range of values that are connected with this quantum dot. But perhaps you can also use some external moving charge to be able to determine the position even deeper. So what I'm saying is that you can try to attempt measurement of position and momentum of this electron by such type of system. So where you have Josephson junctions coupled to a system of two semiconductor quantum dots, and there is external passage of a charge. So that's possible attempt. So you need to monitor the change of Josephson junction state and the change of moving charge state, and then you can have some hint on what was going on in the system. So if we are able to formalize such description, and I believe we are able to determine, we are able to, so we can attempt, digging into quantum mechanics foundations with trying to answer what's happening to the quantum system if both position and momentum is measured. That's at least that's kind of answer I might have that is translated into nanotechnology. All right, maybe very last few things. So basically, yeah, so you might use various types of Josephson junctions. So you might have this, okay, the qubits were here was linear position-based qubits, as I described here. So you have two coupled qubits, and you can couple to external Josephson junctions. That's on the scheme. Or you can create a kind of Roton-like position-based qubit. And here magnetic flux will be quantized. And this magnetic flux can interact with a Josephson junction with a closed loop. So you have superconductor that is separated by insulator. So this system interacts inductively and electrostatically with this semiconductor qubit. So you can think about such type of experiments. So that's what I have. All right, maybe very last thing that I might mention to you. I know that everything starts to be pretty lengthy today. Yeah, so just to describe you. So this is one of my archive paper that's right now under publication, but it's still okay. So basically, you can have all things that I have discussed today, but I just want to mention the very last aspect. All right. So this is more or less what I described today. Let me go to the very last section. So in the last section is we have this Roton qubit. So we have a situation where we have a nanowire, semiconductor nanowire, and then there's a possible gate on the top. So then there's some barrier for electron. So then moving the charge can induce also magnetic flux. That's quite important to note. And yeah, we can exercise this case by so here also the very simple analytic model can be constructed. The story is quite technical, so I'm not going to tell you in greater detail. And just to mention to you, there is the whole zoo of qubits topologies that can be used for such type of experiments. They are described by figure 8, and basically that's it. So my open type of I'm trying to construct the scientific grant for possible construction of quantum detectors with a single electron semiconductor devices. Those devices can be highly integrated. So I believe both physicists from CERN could be interested in such thing. Physicists observing the solar winds supposed to be interested as well. And also semiconductor industry shall be interested, since the CMOS technology can be utilized for the usage in quantum detectors and quantum computation. So my claim is not so deep with quantum computation as claim of Google and IBM, therefore, in my kind of modest approach, I would suggest, I would like to find allies for scientific collaboration in constructing of new type of quantum devices, and also in fundamental description of them. So that's a message from me. Thank you, and please give me some questions.
Can you put link to this paper on the chat so that
Yeah, sure.
Download it?
Sure. I will.
Okay. All right.
Second. So you think this topic would be interesting to you? Like,
yeah. Okay. Another question is, you said you associate the magnetic field with this oscillating electron between two quantum dots.
yes.
And now the question is, do you have analytic formula really that can be seriously justified? The formula for the magnetic field for a given state of oscillation?
Yeah, I can prepare such formula. Yes, basically I have. Yes, basically I have.
Okay, but is it just your invention, or is it something that is being already used before? The association.
I am not fully aware about somebody other using it. So let's say I already placed this paper on this chat. I'm not aware of somebody using it. I have certain ideas, you know, how to do a quantum electrodynamics in such type of systems, but I have to admit that mostly I was working on my own. So in a sense that I try to have a coherent reasoning. I see and try to have as analytic results as possible. That's my prescription. But yes, I admit it would be nice if my results or my usage would be
so far is just a theory, yeah, based on you say QED, yes, but yes. No one, of course, ever tried to check whether your formula, yeah, can be somehow experimentally semi checked. Mm-hmm. Not yet.
So yes, that's true. I'm looking for theoretical predictions and for experimental justification. I can say that there are already like people like Fujisawa in Japan, or Peta from Princeton University, that those people managed to produce single electron devices. And there are various other groups in the world like Sackley, but I would say that I was simply, this considerations comes from the fact that I was simply how to say, working on my own at University College Dublin. I was doing quantum description of a quantum system because I was working with electrical engineers. So they basically designed the circuits. So I was trying to create a theory for them that describes the behavior of these circuits and try to look for a quantum features as electrostatic entanglement or entanglement between matter and radiation, or a quantum communication. So essentially, I have achieved those targets by usage of tight binding model, but still it would be very nice to confront some of the results with more experienced researchers than I am, and it would be nice to proceed with that.
Thank you.
Yeah, so do you have, Professor Jacek, do you have any kind of maybe possibility of giving your talk on these issues that you mentioned last time? So could you think of on going deeper into the problem that you described last time?
I mean, what kind of question you would consider most interesting? Because of course there are many directions.
Yeah, so let's say it would be lovely if we can translate this these fundamental questions
Yeah,
into design of new experiment, right? And so we don't need to answer them directly. We can simply design the experiments and make a predictions. If scenario A is valid, then predictions are like that. If
Yeah.
scenario B is valid, their predictions as that. And then people could be motivated, you know, to test these things in greater detail, right?
I think that you see, because probably one of the most closely approaching experiment of my applications of theory of quantum measurement that I was working on was a different theory of Josephson junction connected to radio frequency circuit, right? You can couple classical radio frequency circuit to the quantum Josephson junction, and you have a clear case of a classical system. This is just, you know, coils and condensers, more or less, okay?
Yeah.
Coupled to okay. And from what I was doing, but it was years ago, okay, was a better theory than very primitive theory that was used by people doing experiment with. Because when you play with this coupling between classical and quantum, you essentially you can observe quantum jumps. You measure the classical current, and it's and you see jumps, okay, in this current. Probably you can do something similar with quantum dots nowadays. So I would have to look again, maybe if you can give a link to the most understandable paper dealing with something like what you were talking about, okay? In your case, you have this oscillating electron, which you consider as a quantum mechanical system, but the magnetic field that you think it generates, right, is essentially the classical magnetic field, which is measured, yeah, by.
Yeah, it's very interesting that you see. Of course, we used to we used to think about this. So we can have a wave packets going in both directions, right? So each of wave packet can generate the component of magnetic field that has opposite values. So in a sense that we can think about even quantization of magnetic field by such structure, right? I was thinking about that. So even I was thinking about, you see, you have two oscillating electrons, and the classical theory of there's for classical charging balls, if they oscillate, if there are two balls on the springs and they oscillate, they will emit electromagnetic radiation, right? And after infinite time, the oscillations will stop. That's a classical picture, right?
Right.
But in a quantum picture, I would say still I would expect that certain energy will be emitted to the space because of these oscillations. But maybe there's some threshold of energy that cannot be emitted anymore because of uncertainty principle. As so this problem is a bit similar to the problem of electron and proton. So in classical description, the atom lifetime in classical picture is finite because electron that is moving around the nucleus is moving with acceleration, so it should emit electromagnetic radiation. But because of uncertainty principle, this emission of electromagnetic radiation is kind of compensated by Heisenberg uncertainty principle. I never have seen very exact calculations done with that, but still, I somehow believe in this argument. And still, the same question can be addressed here, since we can have injection of electron to a two quantum dot system. We can inject also hole instead of electron. So in various ways, we can create the matter that has, and then we can test quantum mechanics in various aspects, right? So I was thinking about even a quantum electrodynamics with such type of systems, but still, I have to admit that so far I work on my own, since I don't have allyship with some nice physicists. So that's why I really would appreciate if you would be interested in such type of problem. Then it would be nicer to to do something together, right?
Okay, we'll continue thinking and exchanging ideas.
Was it clear, this description of co-measurement of position and momentum to you? Was it clear? Is it understandable what I mean? Or
I got a pretty good idea. However, I am not very happy with the way you would like to get the analytic formula for this magnetic field, going to quantum electrodynamics, because I think it will complicate completely unnecessarily.
Doesn't have to be. No. There was just extreme version. I still believe in first approximation, this magnetic field could be of quasi-classical description. That would be sufficient.
Yeah. Okay. Yeah. And
so what I'm saying is that external moving charge particle can probe electron position, right, in a chain of, and at the same time, this so you need to monitor the external moving charge particle at the same time with a state of Josephson junction. And Josephson junctions are amazingly developed those days. They have, they managed to measure phonons existence between two superconductors. They are really extremely well developed. So the question is, how to design a nanostructure that will somehow, give us this question, how to do it, and then we can.
In fact, it's the story is even more challenging, because what the interesting question is not whether you can measure simultaneously position and momentum, but what will happen when you repeatedly measure position and momentum, and what kind, because if you repeatedly measure position, then essentially next measurement will give the result not too far from the previous, because the particle has a finite velocity, cannot move too far. Usually we say if we measure a position, right, the next instant of time, the particle will stay at the same position unless there is a reason for it to move, right? Like spreading of the wave packet or external field, right? So, but if you measure position and momentum simultaneously, one measurement will disturb the other measurement. Okay, that's our heuristic reasoning. We don't know how it will disturb, but question is, after you do repeating measurements, whether you will see certain pattern in this measurement, or you will get complete chaos, because the distortion is unpredictable, and you will not see any regularity. But so what I say, that if you even invent simultaneous measurement, it's okay, but can you do it repeatedly in a very short time? Okay, that's another question and technological challenge.
Okay, my first answer would be a kind of slightly optimistic, yes. If you have a stream of protons in accelerator beam, one is just one after another, right? They are very moving with almost the speed of light, right? So this could somehow correspond to your very quick instant measurements of position, right? Something like that. You can also translate, you can also design external nanostructure with some moving charge that is able to do similar things. And so I believe this is somehow possible. This is somehow possible. That's my belief.
But I want it to be done on the same quantum system.
Yes, absolutely, absolutely. No. Yeah. That's what I'm thinking. Okay, so in a sense, I have already nice kind of motivation. So I would try to deliver you some proposals of some possible nanostructures, topologies, and
okay.
And then we can think how to deal with that. So we can think what we can compute theoretically and what we can propose, what type of experiments we can propose to the experimentalists, right?
Okay. All right.
Yeah. So if you have some nice topic to be presented, please let me know. So,
Right.
I'm looking for a new speakers right now. So, yeah, it's up to you if you have some nice proposed topic to be given,
Okay. Thank you.
Thank you too. All right. So, are there any more questions or comments? So, thank you today for very excellent topic of presentation by Dr. Marcin Kowalik on machine learning in cryogenic systems. And thank you for a very nice discussion and for listening to this, also to the second seminar on quantum metrology. And so I plan to continue these seminars. So I'm looking for the speaker for the next week. So please, there is already a quantum system, hardware system channel on YouTube. So I'm placing some recordings of the seminars. And also, so please invite everybody that might be interested. And I hope we can meet on coming week. So have a nice weekend and see you next week.